Okay, so I'm just going to give a general overview of the comparison between the two cases, and I'm going to say some things that I haven't justified, and hopefully I'll have time to talk about them later because they're really interesting. So things we have, so we have spaces, we have bundles, so we have characteristic classes, so these are the things I haven't talked about. Classifying spaces. Okay, so I'm going to make a table here. So I'm going to call this sort of topology or geometry or something like this, and here homotopy theory. Okay, so our spaces in topology are manifolds. So let's have slash geometry. And our spaces in this homotopy theoretic version we're trying to produce are going to be CW complexes. So slash P spaces. So for our bundles we had vector bundles. For our bundles here we had spherical fibrations. So they're not technically bundles, in that they don't need to be fiber bundles. So our characteristic classes here, so I mean we've got a lot, but I'm going to make the claim that really Stiefel-Whitney classes are characteristic classes of the underlying spherical fibration. And then things like the Pontryagin classes are invariants of the vector bundle. So this is sort of the moral reason that Stiefel-Whitney classes are homotopy invariant, whereas Pontryagin classes aren't. So we've got classifying space BO, and we note that the homotopy groups are infinite. So this sort of all falls out from, I don't know, calculations of Bott periodicity and things like this. And here we have classifying space BG, and in fact pi star of BG is finite. So there are fewer sort of invariants, if you like, of spherical bundles, but they're very hard to compute because you can show that this is actually the stable homotopy groups of spheres, which we don't know how to compute. So I've already said there's a sort of a forgetful map. So it takes a manifold to P space, it takes a vector bundle to its associated spherical fibration. It's not really the same analog case there is here. So it takes a map from BO to BG. Okay, so then we've got this this object that we've been interested in for a while now in this course, the stable normal bundle. So vector bundles, manifolds have a stable normal bundle, and I just mentioned a few properties that the stable normal bundle possesses. So the correct analog for Poincare, Poincare duality complexes is going to be so P spaces have a Spivak normal fibration. So the first thing to note is that these are both stable objects, and they're going to have sort of concrete realizations. So we can always embed this manifold to get a concrete realization, and it's going to be the same for this. So now I'm going to define what this actually is. Okay, so definition. So let's say for X, a P space, with orientation character, board, orientation character, so let's say I want X to the 2. Okay, so a K-1 Spivak normal structure. This is going to be the analog of the sphere bundle of a K-1 normal bundle. Spivak normal structure is, set it on X, is a K-1 spherical vibration so let's say something like this, taking X to classifying space here, or written another way, do that to X with the same orientation character. Such that, so there exists a pointed map, which I will suggestively call C, from the sphere of this dimension to the Thom space of the spherical vibration. Remember, this is the cone on the mapping cone, which agrees with the Thom isomorphism. So we've got a spherical vibration, so we've got a Thom isomorphism. So in the following way. Okay, so it's a P space, so we've got a fundamental class, and this is going to live inside the nth twisted homology. So this is going to be U, so U is going to be a choice of Thom class. So if you look into the proofs of the Thom isomorphism theorem, there's two choices of Thom class, plus and minus. So this is capped with the push forward of this class. So it's got to agree with Thom isomorphism in this way. So as I said, this lives in the nth homology of X with twisted coefficients. Okay, so I've defined something that certainly should have a lot of properties of sphere bundles or vector bundles. So I'm going to check that it does. So example, sanity check. Okay, so let's say so manifolds admit a Spivak normal vibration. Oh, I guess technically some point causality space homotopic to the manifold admits a Spivak normal vibration. So what should everything be? So the sphere bundle should be, so we take a representative as before of our stable normal bundle. Then we're going to take the spherical vibration to be, so we're going to go from, I guess, the manifolds to So this is going to be the normal bundle associated to this, and then we're just going to include that in here. So that's saying just take the sphere bundle. So we had the collapse map. So that took the point compactification of this thing to the Thom space as we wanted. So this is something I didn't explicitly say. The Thom space of the associated spherical fibration is the Thom space of the vector bundle, and that's quite easy to prove. So I've defined it in two different ways, so that should be something that we should be able to prove. Okay, and I already showed that the push forward of this class generates, so let's say the reduced homology of the Thom space. So I want that M plus K. Okay, so for a choice of Thom class, of, I don't know, this thing. So we're going to call that U X. So this lives in H, let's recall lives in HK, that's right, reduced HK of the Thom space. Twisted. Oh yeah. Upper K and also twisted. We have exactly what we want. So this should be plus or minus the cap of this with the push forward. Okay, and then, as I said, there's an ambiguity in the choice of Thom class, so we just choose it to give the positive sign. So indeed, I've defined something that makes sense, and sanity check complete. Okay, so why is this so important? Well, the first reason it's so important is this. So I didn't actually define a Spivak normal bundle, did I? Okay, let's do that down here. Okay. So definition, given a K-1 Spivak normal structure, the stabilization, so normal structure is going to be, I don't know, nu x again. So the stabilization nu x, taking x to bgk, and then including that. This is a bit inglorious for the definition of it, isn't it? Including that into bg. So the stable version of any K-1 Spivak normal structure is called the Spivak normal fibration. This is the Spivak normal I'm sorry?
You said it's the Spivak normal fibration.
Okay, well I'll say the inverted commas. It's unique up to some point, and I'm not really going to discuss that. So let's say a Spivak normal fibration for the time being.